Our next speaker is Asya. It's a pleasure for me to introduce her. She's from Boğaziçi University and pursuing her double major in mechanical engineering. Today, she will give us a talk on natural language processing, and she will show that mathematical structures behind the language models like ChatGPT, which have been very popular lately. I mean, it's really popular, 2 talks in one day. And again, transformers are all we need. Please enjoy the talk.
Okay, hello. I'll talk about natural language processing. So I just want to give a warning. I'll just give a big overview and I won't really go into detail. So if you have any questions, you can find me after my presentation. And I'll try to make this as complete as possible in 20 minutes. So I'll start my talk with a really primitive algorithm. It's called naive Bayes classifiers. And these classifiers approach the problem of classifying a document in a very simple manner. So you have some training data about some movie reviews, for example, and you want to classify these reviews as either positive, negative, or neutral. And what you do is, from your training data, you add all of the words of the positive reviews, the negative reviews, and the neutral reviews into a bag, and you count them. And then you just calculate the probability of a given a class, what's the probability that it fits this class. So rather than calculating the probability of given a document, what's the class of it, it calculates, like, it applies a Bayesian transformation to it, and then it calculates the probability of given a class, what's the document. And I actually coded a naive Bayesian classifier on my own time. Right now, it had 75% accuracy, which is really good if you think about it, because all we're doing is just counting some words and calculating basic probability. And there's some pre-accepted stuff in these classifiers, like we accept that the features that we give to the algorithm are independent of each other. And so that PB part is the same for, yeah, we're talking about the same document, so we can just drop it. And you can make this classifier a bit more complex by, like, ignoring the common words such as a and the, or you can add a not prefix in front of the words which had doesn't, didn't, and stuff like that preceding it. I want to talk about a bit about generative versus discriminative classifiers. So the naive Bayes classifier was a generative classifier, and logistic regression is a discriminative classifier. And the difference is this. Let's say that you want to differentiate between a picture of a cat and a dog. You want your algorithm to say this is a dog and this is a cat. So if you train a generative algorithm, then that algorithm will have some kind of an idea about what a cat is and what dog is. And from that, you can ask it to generate something. You can ask it to draw me a cat, and it can draw something that resembles a cat at least. And like in the naive Bayes classifiers, like you can look at the training data and you can say that, like, words such as good and fantastic were used a lot in positive reviews, and horrible was used in negative reviews. On the other hand, discriminative classifiers don't really care about what cats and dogs are. All they care about is discriminating. Yeah? So, for example, a discriminative algorithm might say a dog has a collar and a cat doesn't, and that's it. It doesn't need to know anything else. As long as it does the job, it's enough. And logistic regression is like the main block of neural networks. It's really simple. You have some inputs shown with X, and you have some weights and biases, and then you put these, you multiply it with the weights, this inputs can be a matrix of different features and stuff like that, like the positional features and some other predetermined features. Or it can just be a simple vector. And then you put it into a sigmoid function or a softmax function, depending on if it's like multidimensional or not. And the reason why we do this is since this multiplying by weights and adding biases doesn't really give us a probability distribution, and we want some result that's between 0 and 1, something that at least resembles a probability distribution. And in order to calculate the weights and biases, we define a loss function. It's also called the cross entropy function. And then we just calculate the gradient and go from there, and we define a learning rate. So thankfully in logistic regression, the loss function is convex, so that we know that it has a minimum point. So with the learning rate, it will shift until it comes to the right place. And now I want to talk about a bit about vector semantics and embeddings. So let's say you have some documents of Shakespeare, and you can look at the term document vectors. And then from just these, like from here, you can see that you can say that Harry V and Julius Caesar are really similar because they use similar words. And As You Like and 12th Night are also similar, so they use those words. You can come to conclusions like that. And for example, you can look at the word by word matrix. So you define some n, it might be 4, and you look at the forwards before that word and forwards after that word. So you look at, you count how many times they were used together. And then from this, you can calculate that digital, and here it says information. Digital and information are very similar. On the other hand, cherry is not. But when we do this, we get really long and sparse vectors. So in order to solve this, we use embeddings. And in embeddings, our main goal is to create dense and short vectors. So word2vec is an algorithm to solve this. And what it does is it defines vectors. And after defining a vector, it iteratively shifts all the other vectors so that the data that we collected on the other page fits into that description. And again, we define a learning rate to define how much it will move. So it iteratively loops through all the words. And in the end, you get something with only 50 dimensions. On the other hand, we have a dimension as how many words there are. And from these embeddings, we can create some really interesting conclusions. So there's something called the parallelogram theorem. So if you have the king vector, man vector, and woman vector, you subtract the man vector from king and then add woman, and then you'll get queen. So these embeddings carry the meaning in a way, but it also carries some kind of prejudices. So for example, if you say computer science man, and then 12 woman is, and then it completes it as a housewife. Or if you have some Italian name like Fabienne, it will have more similarity with words like pizza and espresso, while an American name will be a lot more different. It can have some racist or sexist stuff, since those are in the training data. And logistic regression is great, but it's not really enough. And the reason why for this is there's something called perceptron, and it's a really simple logistic regression which assigns 0 or 1 according to some weights and biases. And this perceptron is not able to define the function ZOR. So it can define and, it can define or, but it can't find the correct weights and biases in order to calculate ZOR. And the solution to this is to just add more logistic regressions. So in a way, add a hidden layer. And then when you add a hidden layer, you can calculate functions more complex, such as ZOR. So neural networks and neural language models use these hidden layers, but the process is the same. In the hidden layer, again, you multiply it with weights. Now they're multidimensional, and add some biases, and then you put them into some activation functions. These can be the sigmoid function, the softmax function, the weight function, changes according to what you want to do. And then you calculate the output layer, doing the same thing again and again. And while calculating the weights and biases, now we use backward differentiation and the chain rule. So we define the same loss function, and then we find the last layer, and then we pass the gradient down using the chain rule. We calculate the weights and biases. And recurrent neural networks are a more special type of network. So the network that I talked about was a feed-forward network. And the only difference of RNNs is that the hidden state is fed into the algorithm in the next step. So, and this helps us in a way give some kind of context. So if you have some text input, the first word will create some hidden layer, and that hidden layer will keep on affecting while parsing the other data. So it has a lot more information in that. And like if you unroll all of the hidden states, you'll again get a feed-forward network. It just seems to have a lot more input. And RNNs are used a lot. So you can use it for part of speech tagging, which says like, this is a verb, this is a noun, and stuff like that. You can use them in order to, you can stack RNNs on top of each other in order to get better results and make more complex algorithms. And like the output of one RNN is the input of the other one. And you can classify sequences in a more complex way, like I said, positive, negative, or neutral. And one of the most popular areas of RNNs are encoder to decoder things. So given a text input, the encoder creates a context vector. This is a simple vector. And then when you put it back into the decoder, you get some new kind of output. We can use this for example, to translate between languages. So here's a Turkish sentence, and then the decoder gets something in French, and you put it into encoder, creates a context vector. Then we get it, and you can use it for summarization and stuff like that as well. So it's really powerful. But RNNs have some kind of problem. We are asking it to do a lot, and it has to calculate the input given the old states, and it has to remember what happened before. But since we only give it the last hidden layer, it starts to forget. So when you give it some really long text, it has some difficulties. The solution to this is long short-term memory, LSTMs. And the difference between RNNs and LSTMs is LSTM has gates. There are 3 gates: the add gate, the forget gate, and the output gate. So the forget gate is like the forget gate tells the algorithm that, okay, the subject is dropped, you can forget about this. The add gate adds like, okay, this is the main focus, remember this. And the output gate is for the calculating the next layer. But this way it becomes even more stronger. But LSTMs sometimes have a problem. So again, the last hidden layer has too much power. It has to carry all of the information in the previous text, and then you have to decode it. So the solution to that is, while creating the context vector, we give it all of the hidden layers, not just the first step, second step, third step, stuff like that. So it becomes even more powerful. But like the downside of making it more powerful is that it becomes extremely hard to compute. And transformers have a solution to that. So the power of transformers is that it computes stuff in a parallel way. So it has a self-attention layer, and it computes all of the inputs. Like in the first part, it has only the first input, and then it processes that. And the second part processes the first and the second part together, and it goes on like that. And the advantage of this is that when you have some kind of long data, you can compute it a lot faster. And while doing that, it has key and query fields. So it tries to get the key concepts of the data and how the words will affect the query. And then all of the calculated things in the self-attention layer are put together. And sometimes even one self-attention layer is not enough. So we have multi-head attention layer. And this is just multiple layers so that you can, if like a text has a lot of different subjects that it talks about and different things are connected in different ways. So you want to use multi-headed attention layers. And in the end, you get the transforming block. And this is the thing that's really powerful stuff like ChatGPT use. So it has the self-attention layer, then we use the residual connection between the steps so that we don't really lose the data. So since self-attention layer of the feed-forward layer, they really change the text. And in order to remember it, we add residual connections, and then we normalize that as well. And then we get some kind of output. And while working on this, we also looked at proving stuff using natural language processing algorithms. And I read some very different articles, and it's a promising field. And like here's a graph that shows how well did the algorithms do in different kind of subjects. And I also called it a simple algorithm, which given a question, it tells you what fields of mathematics you need to learn in order to solve it. So it doesn't solve the question, but it says like you need to know group theory in order to solve this question. But I didn't have that much data, so I don't know how accurate is it. But like when I tried it, it had some good things. So thanks for listening. If you have any questions.